as David mentioned, as I'm hearing, there has just been an operator talk explaining operators, which is great. My talk will be focusing on an actual project where operators have been used to achieve business goals and to automate a really complex CI/CD system. So let's get into it. First of all, this is not a really crappy slide. This is actually Xcali Draw. I will be drawing live today. So for the first few minutes, I actually have like pre-prepared stuff because you don't want to see me drawing that figure live there. So my name is Adam Sandor. You can find me on Twitter under this handle. I used to work for Container Solutions, same as David. So it's a really nice coincidence to meet here today. About a week ago, I started at Styra, the makers of the Open Policy Agent. But this talk still comes from my Container Solutions life, one of the biggest projects I did at CS. So the goal of that project was to automate a CI/CD system for a large German enterprise company. And we did a lot of the work there using Kubernetes Operators. And this is the angle I will be explaining operators from today. So yeah, I actually have a list here of things I'll be covering. So why infrastructure automation, and actually why Java? We have used a lot of Java in our operators. The CI will explain the CI/CD platform that we built just a little bit, because that's actually how the platform actually works is not the focus of today's talk. I need to explain it a little bit to understand what did we need to automate, but the focus will be how is an instance of this system being spun up and how is that automated. So you will have to bear with me for a really quick explanation of what the system actually is. Then I will be explaining a bit on Kubernetes operators, what they are, and the Java Operator SDK that we developed during this project to help building operators in Java. For those who are here and are not Java developers, don't worry. Actually, like 90% of what I'm gonna be saying here, maybe 95, is totally applicable to any other programming language, be it Go or Python or whatever. It's gonna be pretty high level. I'm not going to be going into like Java features. How we created our operators and a bit of Q&A at the end, of course. So first, just a soft kickoff here. We live in the world of, or in the age of clouds, and with that, in the age of APIs. What this means is we have unprecedented powers of doing things when every piece of our infrastructure can be automated, can be managed using APIs. We can write code that interacts with these APIs, and we can do things that were either completely undoable before the age of clouds and containers, or that or maybe some things were doable but were really difficult to do, and now they're easy. However, this doesn't mean that our lives as either operations or infrastructure people or software developers, that our lives have become easier. Because every time we invent something new that makes all things easy, then suddenly new requirements come on. Suddenly the expectation is now that everything is going to be automated, and we actually have to write all that automation logic somehow. So it's no longer acceptable to like spend 2 hours on logging into a server and installing some I know, a web server, and then putting some Java application inside that and so on. That's like that used to be an important job to do. Now that's not acceptable that somebody would have to do that job, because it should all have been packaged into a container already and running on Kubernetes in 2 minutes. So with this in mind, Kubernetes operators are offering a new and really exciting way how to develop that automation. So that's and why it's important to realize where we are now in the world is that Kubernetes operators are actually pretty complex things, and they are not that easy to write as a lot of other stuff. Like, I know I can spin up a Kubernetes cluster with Terraform really easily, but building an operator is still a pretty involved job in many cases. However, what these operators allow us to do is much more than what we can achieve with Terraform or Chef or Helm, for example. So that's why we are actually willing to pay the price that those operators require. All right, let's jump into the CICD system that we built that later we needed to like automate the provisioning of. So it's a large enterprise company. So whatever I write here basically needs to happen for like 100 teams. So otherwise it's not nothing really fancy, but like when you multiply this by the number of teams, suddenly everything becomes more difficult. So basically the company was moving to an OpenShift based platform. So we had a lot of OpenShift clusters, basically an OpenShift cluster for each stage in the continuous delivery process. For those who don't know, OpenShift equals Kubernetes for the purposes of this talk. It's basically Red Hat's Kubernetes distribution, and it has extra features compared to normal Kubernetes, but I will not be even mentioning any of them during this talk. They're not important for what we are discussing here today. So we had a bunch of OpenShift clusters: the Dev OpenShift cluster, the Staging OpenShift cluster. I will put the production there and then I will stop. There were multiple production clusters, and it's been more complex than this, but this will explain it well enough. And basically what we needed to do was on each every development team needed to get their environment on each cluster. So basically if we had like team X, then team X had a dev environment on the Dev OpenShift cluster, and there's going to be a bunch of copy pasting here before we're done with this, but I need to do this to like to really illustrate what's going on. By the way, I'm doing this live drawing, just if you're wondering, because it's kind of more fun for me, and hopefully it's a bit more engaging for the audience, so fewer people fall asleep during the talk. And these environments basically need to be controlled somehow. And we really went big time for GitOps while controlling these environments. So there is a bunch of Git repositories in not GitLab. Geez, I forget the name of the Git. Well, let's call it GitLab. Maybe I'll remember the real one, but it doesn't really matter. So the every environment for every team, and of course here we could have another team, right? So we could have, I'll put this underneath, so I have some space here. Team Y dev, right? So like every cluster would include other teams also. So all the teams would be represented basically on all the clusters. And now there would be a team X dev repo in GitLab, in the Git repository, and that would have all the YAML files. So inside here we have YAMLs. We have all the YAML files that control the team X dev environment. So this is like pure GitOps. And we would have a bunch of these repos for every team again. Oh, sorry, no, this is team X, staging repo, team X, prod repo, and then, so what we need to do is we need to sync this development repo to this development environment. And what we did, we could use Argo CD or Flux these days, but this was back a few years ago, and Argo CD was like not very mature. We didn't trust Flux for some reason, and so we opted to do this with Jenkins. So we had on every cluster a single, we can call it the GitOps Jenkins. So this Jenkins would have a pipeline for every team, downloading this repo and applying the changes to here, basically. And also, that's important to note, there's a GitOps Jenkins, but there is also every team got their own Jenkins in their own development environment for building their own, like this would be the CI Jenkins. So in the end, what we need to provision for every single team is a variable number of environments on each cluster, because not every team had an environment on every cluster, so that's configurable. We need to configure, we need to create a Jenkins for them in their development environment, and we need to create a bunch of Git repos in, not GitLab, but the Atlassian one. I still can't remember, and I'm doing this talk for like the 10th time, and I know I'm just blanking out there. Sorry about that. Again, doesn't really matter. So, and finally, we have to put a sync pipeline into this Jenkins. So like for every single environment, there is going to be a pipeline that runs this synchronization process to the actual environment. So downloads the YAML files and does kubectl apply, basically. A bit more complicated than that, but not by much. And now our challenge is that whenever a new team comes to us and wants to either get just a new environment or like a whole CICD system because they have not yet been onboarded on OpenShift, we need to create all this. And we tried to first, we were thinking about doing that with Terraform, and we failed for various reasons, not because it would be impossible to do this with Terraform. Basically, the biggest problem was that much of what we are doing here, like creating a pipeline in Jenkins or creating a Git repo, was not supported out of the box by Terraform. We had mostly Java developers on the team. We couldn't really extend Terraform. We didn't know it that well. So in the end, what we did, we just wrote some Java code that actually talks to all these APIs, to the Jenkins API, to the Git API, to OpenShift and so on, and created all these things. So that was great. We created kind of a command line tool, but it was not enough because the command line tool had to be launched from somebody's laptop, basically. We needed something server side that could actually like store what it did, maybe continue if it gets interrupted, modify things and so on. Because we, well, at that point when we were like that early in the automation journey, we had like a wiki page to track what teams have what environments and so on. So that's clearly not sustainable once we were past like the 5 teams that initially got onboarded. So here come operators. First of all, what are Kubernetes operators? I need to do a real quick intro to that. I'll do the short version here. If we look here, and this is now I'm drawing a different picture, so it's gonna be connected with that other one, but it's still going to be a bit of another thing. We're zooming in on a single cluster here right now, right? So this is the OpenShift cluster here, and this is one Kubernetes or OpenShift cluster up here, and that has an API server. So there is the Kubernetes API server here. And the API server serves as basically a key value store for all kinds of objects. And whatever object is put into the API server, Kubernetes will try to actually create it in the like real world. So let's say we create a deployment in here, and then Kubernetes actually creates pods and downloads images and makes that deployment happen. But the Kubernetes API server is also extensible. So we can create custom resource definitions that are like custom schemas and of custom objects that are just whatever we dream up, and can define the schemas for them and then put those objects into the Kubernetes API server. So we defined a custom resource. Let's start with maybe just the simplest, the Jenkins here. So if we define a custom resource called Jenkins, and we give it a, we can give this Jenkins some parameters, like it would have a name. They always have to have a name, version, for example, what version of Jenkins do we want to run? And we always specify which team is this created for. So for all our objects, we have like a team-based system. So it's always created for a team. It will then, so when we create this custom resource, Kubernetes doesn't know what the hell a Jenkins is. We told it that it has certain properties and whatever, but we create a Jenkins, nothing will actually happen because Kubernetes doesn't know what to actually do with the Jenkins. The thing that will know what to do with the Jenkins object is an operator. So we create something called the Jenkins Operators that will be running on this cluster, and it will be reading the custom resource. It will be reading, sorry, the API and registering itself, because the Kubernetes API is not just simply a key value store. It actually can, because it supports watches. And basically the Jenkins operator can register itself to be watching any changes to any Jenkins objects inside the Kubernetes API server. So there is a Jenkins custom resource defined, or a custom resource definition, but then there will be concrete Jenkinses. So there I will, at some point, I will create a Jenkins for, sorry about that popping up there. Yeah, that's better. Jenkins for team X with version, I know, 111. So I can say now that I want this Jenkins, and the Jenkins operator, the Kubernetes API server, will tell the Jenkins operator that a Jenkins custom resource has been created. And then the Jenkins operator can just do something with it. So basically the Jenkins operator in here, we are running our own code. This is a pod on Kubernetes. So this is nothing fancy, really, the operator. Kubernetes doesn't even really know about this operator. It just knows that some process running on the cluster has registered itself to get events about Jenkinses, whatever those are. So once the Jenkins operator receives an event that there is a Jenkins, it can go and create the actual Jenkins, which in this simplest case, this Jenkins will be running on the same cluster. So what the Jenkins operator will do, it will go and tell the Kubernetes API server that I want to create a deployment now with the image equals Jenkins 111, which of course will cause Kubernetes. So there is going in the background, hidden inside Kubernetes, there is the deployment operator or controller that will then create pods based on this deployment. So there is like these operators that actually collaborate this way through communicating through the API server. And so once this deployment that creates pods and so on and makes the Jenkins actually run. I will delete this now from here because we'll need the space. Also, I delete the Jenkins CRD, so we just have an example Jenkins there. And move this up here because we'll have more operators. So basically, now that we have a Jenkins operator, we can create Jenkinses, and that's great. We don't have an operator for the name. So what else does the team need, right? So the team needs also a namespace. We don't have an operator for that because that's a built-in Kubernetes resource. So we just create a namespace. I'll get to that in a bit because someone needs to create that namespace, but it's going to be a part of a bit more complex story. So let's just assume there is a namespace. The Jenkins operator, based on what team this Jenkins is supposed to belong to, will know which namespace to create the Jenkins in. Basically, we use naming conventions. So like it will be team X-dev namespace on the dev cluster. Cool. So next thing we need to create a Git repo. So we will have another custom resource, which will be, maybe we can call this a GitOps repo, because it's not just any Git repo. There's no source code in there. There are just YAMLs in there that need to be synced. For, again, which team? It's going to be team X. And I don't even know if we need any other properties for it. Oh yeah, we need which environment does this belong to, because the Jenkins always gets created on the dev environment, so there is no question about that. with the GitOps repo, we need to create a dev GitOps repo. And actually not just that, of course. So we need GitOps repos for team X, dev, staging, prod. Okay, let's just draw the dev and the prod here, because we don't want, we'll be running out of space again. And of course, again, we know the pattern by now. We will need a GitOps repo operator, which will again be a pod. And this GitOps repo operator, when this receives an event, again from the API server, that a GitOps repo custom resource has been created or modified or deleted, then it will go and it will talk to the Git provider, in our case GitLab, to actually create that repo. So in this case, the operator is actually not provisioning resources on the Kubernetes cluster, but outside it. And we can do this because the operator, the code inside the operator is just code that we write, and it can do whatever the hell we want it to do. This is both the power and like the complexity of operators, that we have to write that code, but we can do whatever we want with it. So this GitOps repo operator would actually have the credentials to GitLab. So this is secure. So whoever is creating this GitOps repo custom resource doesn't have to know the credentials to GitLab. The credentials are stored in the operator, and that's created by administrators. So we have a separation of concerns here. So people can request GitOps repos, but they don't have to have like admin credentials to GitLab. This is one of the really nice patterns we can achieve with operators. And it's also time to say a few words about like what's happening inside this operator on the level of, I already mentioned that you can write this operator in whatever language. All you need to do, all this language need to have is a Kubernetes API client. As these are really REST calls and WebSocket stuff for listening to watches, you won't even need to have a real client, but that really helps because the Kubernetes API is not exactly simple. So and a client library really helps, but actually most languages, all major languages these days have Kubernetes client libraries. So as we were writing our operators with Java, our client library is, so on the bottom layer here we have Fabricate, which is a Kubernetes client maintained by Red Hat. That's pretty much, there is another one for Java, but this is the big one, the oldest one. I've been using it like 5 years ago already. And on top of this, there is a lot of common code that happens on inside every operator. So for that reason, we decided to start a project called the Java Operator SDK. You can find this project on Java Operator SDK.io. So if you're a Java developer and thinking of writing operators, please check out this project. It's actually been embraced by Red Hat, so there is some support behind it. It's actively developed, and it's totally usable to help write operators in Java. There are actually people also still writing operators in Java without this, but so it's doable, but it helps to address some common concerns that I don't have time to go into right now. So, and above the SDK would leave like your own code, right? So it would be the logic what the Jenkins operators needs to do, and this stack repeats inside every one of the operators that we have built. So the next operator that we need to create is the deployment pipeline operator. So for every Git repo and namespace pair, we have to create I'll color this here to make it more visible. So these all belong together. So we need a pipeline that executes the synchronization between this and the environment, and we call that the deployment pipeline operator, or the deployment pipeline custom resource and then the corresponding operator. So this would also have a team and environment, same way like the GitOps repo, of course. Yeah, let me just break this into another line. So there would be, of course, multiple one of these, and there would be a deployment pipeline operator. And this one would have credentials to Jenkins, to each and every Jenkins, actually. So Jenkins dev, Jenkins staging, Jenkins prod. So these are all credentials that this deployment pipeline operator has to have. So how to draw this up here. Whoops. Yep. Credentials. So that's the I think I can break this line. Maybe I can't. Okay. I'll just draw a new one here so it doesn't go through there. Right. So the deployment pipeline operator can talk to every deployment, every GitOps Jenkins on every cluster. So there are GitOps Jenkinses on each cluster, one on each cluster. We just need one and we'll create a bunch of pipelines inside it. So the deployment pipeline operator would talk to these Jenkinses here. And this whole multi-cluster thing where the operator actually has to talk to different things on different clusters, I will go into that in a bit, because the GitOps repo operator has it easy, right? There is just one Git provider, but the deployment pipeline operator has to have more information than that. Otherwise, this is again the same story, listening to its own custom resource and executing actions on something. So in this case, the Jenkins API creating pipelines. Pro tip, if you can always avoid trying to do something with the Jenkins API. It's not pretty, but it works in the end. Okay, so we have created the Jenkins, we have created the deployment pipeline, we have created the Git repo using our operators. Now, we need to still create these namespaces, which is easy. But the problem here is that you can see how we need to create one team's environment. Now we have a very good abstraction here, but still, once these operators are running, I can come and create all these custom resources, and it's magic from there. The operators will create all the resources. However, one problem is I do need to create all these resources, and it's quite a few of them, and I need to get them right. Second problem is there is an ordering here. So my GitOps repo actually needs to be created before the deployment pipeline. Otherwise, Jenkins will complain that I'm trying to create a pipeline for a Git repository that doesn't exist. The Jenkins also needs to be created after this namespace actually exists, because the Jenkins is inside that namespace. So to create this extra layer of abstraction that we need here, what we did was, okay, I'll remove these credentials from here because oops, we need the space after all. Yeah, the fun thing about this live drawing is that it's different every time. It's not really repeatable. So we created the abstraction of the team, because that's what we really want to create. We want to create a team. And the team is actually surprisingly simple, even though it contains all the information. The team has a name, obviously. It has a list of members. By the way, those members will be used by the GitOps repo operator to actually assign them to that GitOps repo to have credential to have access to it, and it will have a list of environments. So like list of environments would be dev, staging, prod, but there can be more or less for different teams. Often teams would start with one dev environment and then would get more environments added. And this custom resource would be handled by obviously the team operator. And the team operator would react to a team getting created and create all the other custom resources that we have defined before for the other operators. So the team operator acts as an orchestrator basically for the other operators. So it would make sure that a GitOps repo would be created before its corresponding deployment pipeline. And that's actually quite fun how that happens, because so till now we have seen these custom resources only as inputs for the operators, but they're also outputs. So every custom resource, if you noticed, Kubernetes resources always have a spec and a status part. And so what happens is the spec is already the input for the operator and the status is the output. So what the team operator does, it doesn't just register itself to watch for team custom resources, but it also watches all the other custom resources, so it can like aggregate the information. And what it's really looking for is a change on the GitOps repo, and then it checks what the status is once it has changed. And if the status is like, yeah, okay, or actually we put the URL to Git into the status. But once the status for the GitOps repo is okay, the team operator knows it can move on with its own process of, all right, if this GitOps repo is created, the namespace is created, which by the way, so this namespace is created by the team operator. That's created, then it can go and create the deployment pipeline for it. So the whole process is driven by these operators communicating with each other through custom resources. Nothing is ever in memory. That's very important. Operators can crash, they can die, but they have to be able to just restart and look at the API server, look at what's in there, and continue what they're doing. This is a really crucial thing about operators. This is why operators are such a great, basically it's just a design pattern. This is not even a technology. This is just a design pattern on how to organize the inputs for the code itself, and like how is it all synchronized together. Because once that's really important for this process, there are many things that can fail. So imagine during this process, I create a team custom resource and I expect the system to create all the CICD stuff for this team. But let's say GitLab is down for 5 minutes. I don't want to care about that. And this is why this type of system is superior to, let's say, we could have created a web application that just like I can submit a request and wait for a reply, the web page updates, and okay, it says your environment is ready. No, I create this team and I have no expectations on when does it get actually created. Again, this will have a status, right? So like I can watch the status that at some day, same like you do when you create a Kubernetes deployment or something, you can just check the status and at some point it will be somehow indicating that it's done. So the team operator would watch for all these statuses, would orchestrate all this. And when, let's say, GitLab is down, that would mean that the team operator would create a GitOps repo custom resource and would be waiting, because the GitOps repo operator would have some exceptions in it that like, oh, I tried to create it, but I couldn't. But then it would keep retrying. This retrying functionality is, for example, something we built into the Java Operator SDK. So the GitOps repo operator would rescan the API server, would retry, creating that repo as long as it takes, and someday it will succeed, hopefully. And then it will write the status that it's okay. The team operator will pick up on that. It will create a deployment pipeline, and that status is okay. And finally, when everything is okay, everything is created up and running, then the team operator updates this status. So that's how this like system of operators accomplishes the task that we did. So there are like different design decisions in here. I still have 5 minutes, so I can bit elaborate on some of them. First of all, you might be asking how long this building this system took. Well, it took months and months and months. I think about like 6 months of hard work. It took longer than we wanted it to take and longer than we expected it to take. So yes, it's an asynchronous, networked, distributed system with all the complexities that brings and all the like, yeah, when it's nice that it's resilient, but of course, when something just doesn't happen, you actually have to dig through everything. Why did it not happen? Okay, team operate. There is not going to be an error because there is no expectations that the Git repo gets created in like 1 minute, because we know that whatever something might be happening, the Git repo operator might be down or whatever. It might be 1 minute, it might be 1 day. We don't know. When do we start looking for what the problem is? That's the general problem with distributed systems and asynchronous systems. The second design decision was to split this all up into several operators. On one hand, there are different options. We could just have a team custom resource and get rid of all these others, and just team custom resource drives the team operator, and the team operator does the work of all these operators. That would have been one option. The problem with that would have been that if you go and say kubectl get GitOps repos or kubectl get deployment pipelines, you would not get anything. Basically, all the information would have been stored inside the status of this team of what has been created, what has not been created. That would have been a solution that worked. We wanted to go all out with this to like really have this nice view through the system with kubectl, with like listing all the Jenkinses and stuff. That might have been a bit too far, but it's basically a monolith versus microservice decision. So it has its pros and cons. The other interest, we could have also had multiple custom resources, but then just a single operator. So that would have been also an option. This way we had like a microservice style. We can update the GitOps repo operator without touching the team operator. So again, monoliths versus microservices. The other interesting thing was that we bumped into that where do you run the operators? Many Kubernetes operators that you can download from Operator Hub that are like the Kafka operator for Kubernetes. That's great. It runs, you run it on your cluster and it will create things on your Kafka instances on your cluster. So that's a very clear mapping of like it's managing Kafkas on the cluster. Now with this system, it's not that clear because this system had to centrally manage a lot of OpenShift clusters. So which API server are we even talking about here that has the team custom and all these custom resources? And actually what we did was we run this system on production because it's a production system. So that's where this system gets a namespace on the production cluster. We called it, actually we named the system Caron. And so it's the Caron namespace on production, and that's where we create like team custom resources. So there would be team X custom resource. The deployment pipeline custom resource would be also on production because that's oh no, sorry, not the deployment pipeline, the GitOps repo, because that's not related to any cluster. So GitOps repos would also be created here. But then when the team operator does its work, for example, creating Jenkinses or creating deployment pipelines, these custom resources would be created on that cluster where that Jenkins or that deployment pipeline is running. That means also that if the team operator running in the Caron namespace on production creates a Jenkins custom resource inside this namespace here, that also means that the Jenkins operator is enough to run on this cluster. So the Jenkins operator only runs on the dev cluster, watching for Jenkins custom resources created on any namespace and then creating an actual Jenkins inside that namespace. This is also quite complex because of like multi-cluster management from a single cluster. So this is the other like interesting point I had time to highlight, that we have to make these decisions. So which custom resource actually gets created where does the operator run? And the operator can actually watch multiple clusters. Like the team operator is talking to the API server of its own cluster, but also to the API servers of the other clusters to create stuff, but also to watch for events of those other custom resources. So this is that's also why it took like a good 6 months to build this, because like even adding the multi-cluster fun to it was a lot of work. Yeah, and that's pretty much it. So this system can spin up a team environment just by somebody creating a team custom resource. So I hope this was useful to give you a grasp of using operators to provision your own infrastructure. So there are many different things operators can be used for, like a third-party vendor, like a Kafka vendor, can provide you with a Kafka operator or a MySQL operator or so on, so you can easily run it on your cluster with like more bells and whistles than if you would just do it with Helm. This is a very different use case for operators. This is doing your own infrastructure automation using Kubernetes operators. Thank you very much. And yeah, let's back to the studio.